Hello there, my name is Alec Filson, and today I'm going to be talking to you about using a microwave reactor to make N-heterocyclic carbenes, or NHCs. An exciting topic as it sounds just put like that, I know, but bear with me and you will sort of begin to understand what it is I'm talking about. So, first of all, to understand the importance of why I even care about making NHCs, I need to talk a little bit about energy, specifically how we make it. And currently, energy is made by burning fossil fuels. And burning fossil fuels releases carbon dioxide into the atmosphere. This carbon dioxide then increases global temperatures and acidifies the oceans, neither of which are very good things. So the common response to this has been switch to entirely renewable energy and do so quickly. The issue is switching to entirely renewable energy will take time because we have to build that infrastructure, and in the event that you can't actively generate energy, such as solar or wind energy, the sun not being out, or the wind not blowing as strongly as it needs to spin those turbines, you then run off of batteries which could potentially run out. So what if there was a way that you could have a reserve amount of energy, somewhere where you can get energy if you need it, and that's one use of these N-heterocyclic carbenes. The other is medical use. You can actually use these in antibiotics, but I will discuss that shortly, as well as what I mean by a middle option. So how does one make an N-heterocyclic carbene? Well, we have focused on one specific N-heterocyclic carbene called Mebim-py. So you combine benzimidazole and 2-bromopyridine, as well as potassium carbonate, mix those together in a tube, and traditionally what has happened then is heating by reflux. Heating by reflux takes between 12 and 18 hours to synthesize Mebim-py, and the issue is that that's a long time to make a little bit of ligand. So what if there was a way that you could do it a little bit faster? And indeed there is. If you use a microwave reactor, which works the same as your household microwave in the sense that it uses microwaves to generate heat, you can, in as little as 5 minutes and as much as 20 minutes, make Mebim-py. And as you can see, we've used different solvents, either no solvent or DMSO as our solvent. These are the two that we have the best results with. And you can see that you actually make a decent amount. So to further prove that we've made Mebim-py beyond a shadow of a doubt is we've used NMR spectroscopy to confirm our results. You can see by this structure of Mebim-py, you can see blue and green circles overlaid, and those correspond to different peaks on this graph. The peaks that aren't labeled are just excess benzimidazole that was left over. So what does all of this say? What's the point that I'm trying to get at here? Well, this serves as a proof of concept. If we can synthesize Mebim-py, it's possible to synthesize other N-heterocyclic carbenes in the same manner using a microwave reactor. So then once you have all this ligand, you make a bunch of it. What can you do with it? Well, as I said before, there's medical applications. You can complex these NHCs with silver and make potentially a replacement drug to silver sulfadiazine, or you can use these in fabrics and give them an antibacterial property, again, when complexed with silver. The other use of these NHCs and the potential use that my lab is exploring is use as a catalyst. So if you look at this cycle that I have drawn up here, you can see that CO2 is being reduced to carbon dioxide, or carbon monoxide rather. So this process takes quite a bit of energy. And to reduce that amount of energy where it's a feasible and effective process, you use a catalyst. The catalyst is made by taking an NHC, sort of like Mebim-py that we've made, and complexing it with a metal. And that catalyst assists in lowering the amount of energy in this needed to make carbon dioxide become carbon monoxide. So what can you do with that? Carbon monoxide you can take to a fuel source. That fuel source can then be used in a car, a factory, wherever you use fossil fuels. This releases CO2, but that CO2 is then recaptured, brought back into this reaction, and this cycle continues on and on. So why even care about this cycle? Well, you create what is called a carbon neutral cycle. There is no net carbon output into the environment, which is what we seek to do by switching to renewable sources of energy. So, with all that being said, that is the potential of N-heterocyclic carbenes. In fact, that's just two of many, many potential uses of these NHCs. So while I have the time, I would like to give a couple thank yous before I go. Thank you to the University of Central Arkansas for allowing me to do this research and present to all of you. Thank you to my fellow researchers, Layman, Alexa, and Rebecca, who without them, this poster would not be possible. And of course, a thank you to my mentor, Dr. Marcia Massey, for her continued guidance and support. Without either of those, I would not be able to put together this poster and give you guys this information that I have. So with all that being said, I would lastly like to thank all of you who have watched this. Thank you for giving me your time and listening to me talk about some pretty interesting chemistry. So without all that being said, I hope you all have a very wonderful day.